Listen. The standard vector. The standard vector in this coordinate system can be a rho small a rho, carefully, plus a phi small a phi, where a rho and a phi are the unit vectors. The directions of a rho and a phi are not unique. The directions of a rho and a phi depend on where we are defining these unit vectors. Definitely, a rho and a phi, wherever you take, are two mutually perpendicular unit vectors, because of which the magnitude of this vector can be calculated using capital A rho squared plus capital A phi squared, taken under root. Because they are two mutually perpendicular components. But the direction of this particular vector cannot be determined if the location at which this vector is defined is given. Carefully. A rho and a phi are standard unit vectors, orthogonal unit vectors in circular coordinate system. These unit vectors have no unique direction. The directions of these unit vectors, when they are mutually perpendicular, depend upon the point where they are defined. Because of this only, there is no general vector from any point in this coordinate system to any other point. Given rho naught, phi naught, and rho 1, phi 1, we cannot define a vector from one point to the other point looking at this only. If there is a vector field quantity, maybe I'll speak about that now. Listen carefully. A given vector can be the position vector of a point with respect to other point, which is the displacement vector. Initial point will be there, final point will be there. If I draw a vector from here to here, it's a displacement vector that actually goes from the initial point to the terminal point. That will have the magnitude and direction. But the vectors in the vector fields, like acceleration due to gravity. Acceleration due to gravity is 9.8 meter per second squared towards the center of the earth. It is not a line. It is represented by a line of length 9.8 meter per second squared. But it is there only at that particular point. We call it as a vector. Field vectors are not the vectors that go from one point to the other point. We just say this is the magnitude and this is the direction of that vector. We represent that particular magnitude by using a specific length. We would have taken a scale. Every length corresponds to a particular magnitude. Length of the vector is directly proportional to the magnitude. So there will be a scale. And the direction of the vector is the direction of the magnetic field. Sorry, direction of the field quantity, vector field. This vector can only be a field vector normally. It is never a displacement vector from one point to the other point. Can only be a field vector. Ready to explain once again if it is required. Please listen carefully. Can only be a field vector. Initially only, have no unique directions. They are mutually perpendicular. I'm giving the statements. I will explain it. Because of which we cannot define a vector from one point to the other. Carefully listen. What is arrow? How did it define AX? At any point, vector of unit magnitude, AX I'm talking about, perpendicular to X is equal to constant line passing through that point in the direction of increasing X is AX. Arrow? At any point, vector of unit magnitude perpendicular to circle of radius rho passing through that point in the direction of increasing rho. Listen. Let us suppose this is the point. I will draw a circle of radius rho. X is equal to constant line, rho is equal to constant line. In the direction of increasing rho is this, right? At this point, arrow. If the point were to be there at this point, arrow is this. If it is there here, sorry. Arrow is this. Very, very important for us to know this. Direction of arrow can be any value in the range from 0 to 2 pi. For the same radius, at different points, the unit vector will have a different direction. You may be wondering why, after all, then we should speak about the circular coordinate system. It is useful to me. Whenever the field created by an object, by a source, has circular symmetry, Like, if I keep a charge at the center of this, wherever you go in the circle, keep a charge, another charge Q at that point, the force of attraction or repulsion will be along arrow. Wherever you keep, we'll say that the force experienced by another charge kept at any point on this circle for any point is magnitude in the direction of arrow. That's all at that point. You anyway are specifying the point, right? In the Cartesian coordinate system, at different points, the x and y components are different. At this point, it has only x component force. At this point, it has only minus ax component. In between, there are x components and y components of varying magnitude depending upon their positions. But wherever the charge is, the universal statement, if we are there in circular coordinate system, is radial. Field is radial on the plane. In fact, in the space, the field is radial to the spherical coordinate system. Sphere of radius are having the origin at the center we talk about. If the field has spherical symmetry, we have to use spherical coordinate system. Circular symmetry, we have to use circular coordinate system. Normally, no practical field is having that Cartesian symmetry. Normal fields are either circularly symmetric or cylindrically symmetric or spherically symmetric ultimately, because of which these are the practical coordinate systems that we have to use. And deriving a particular expression definitely is simpler only if you have chosen a specific coordinate system in that particular problem, depending upon the symmetry of the field that I'm going to explain anyway in the fields. Moreover, arrow is this. The direction of it is not unique. Only if you say where I'm talking about this, I will immediately say arrow is fine. What is Fi? Is at any point, please see the importance of these two. At any point, vector of unit magnitude perpendicular to phi is equal to constant line passing through that point, in the direction of increasing phi. I will remove this. No, the color is Fi. Arrow I gave. What is Fi? If this is the point, this is Fi. If this is the point, this is Fi, because phi increases in the anti-clockwise direction. This is the point, this is Fi. This is the point, this is Fi. Correct? This is the point, this is Fi. This is the point if this is Fi. Again, Fi is actually a rho is radial component, right? This is radial direction. What is this? Tangential. Perpendicular to the radial line is tangential. Hey, why this field important? When you talk about the magnetic field created by a current carrying conductor, we know that it is there in the form of circles. When the field line is a circle, the direction of the field at any point on the field line is the tangent drawn to that circle, that curve at that point. Here it is a circle, it is a tangent line. If there were to be a point that the center field is radially symmetric, circularly symmetric. Field is only radial component. If there is a current carrying conductor there is no radial component, but there is only tangential component of the field created by that. Because of which we are actually looking into the circular coordinate system. Apart from that, in geometry also, in calculus also, we require this. I'll show you the places where we'll be really comfortable than the other mathematical people to do a particular problem because of the fact that we look into the circular coordinate systems in length. Check it. Listen, I want you to know this. Suppose I have a vector 2 arrow plus 3a5. If it is this point, P1, right? Carefully observe. 2 arrow, 2 units, 3a5. And the vector is 2 arrow plus 3a5. This is the vector. If this is the point at which 2 arrow plus 3a5 is put, 2 arrow is radial line, 3a5 is perpendicular to this line. The resultant is yes. Magnitude is same. Definitely magnitude is root of 2 square plus 3 square, no doubt about it. But it's enough if you can appreciate that. If the phi of the coordinate changes, or doesn't matter, at all points on this line, same phi, the vector will have the same direction. They're all parallel, correct? I think you appreciate it. 2 parallel vectors in the coordinate system is same. They will have the same direction. If phi changes, the direction of the vector will change. 2 arrow plus 3a5, unless you know where it is defined, you will not be in a position to talk about its direction. Check it. Two arrow plus 3a5, listen carefully. They'll make an angle of tan inverse of 3/2 from arrow. What is the angle of the vector? At any rho comma phi, rho naught comma phi naught, angle is phi naught plus tan inverse of 3/2, correct? Radial line is at an angle of phi naught, pakka, correct? From radial line, the angle is tan inverse of 3/2, correct? From radial line, the angle is tan inverse of 3/2. So total angle is it equal to phi naught plus tan inverse of 3/2? So phi naught, if it changes for the same vector, direction will change. I want you to think and check whether it is correct or not, the statement. Yes. The rho naught, arrow will make an angle phi because it is a radial line drawn at an angle phi. From arrow, the vector will make this much of angle. Positive or negative, it can be depending upon the signs of 2 and 3. Here it is taken as positive. If one of it is negative, essentially arrow is negative, they have to talk about the tan inverse formula, right? Right? Negative pi plus tan inverse of, because I want to measure the angle between the rho component as well as this. Typically, listen carefully. A general vector from any point to any point is not defined. Why it is not defined? Carefully listen. In the case of Cartesian coordinate systems, we produce x component by varying only x without varying y. We produce y component by changing only y without varying x. Here, just consider, I don't want to spend much of time here because it's straightforward for us. Let us suppose this is rho naught phi naught. This is the point rho 1 phi 1. I want to define a vector like this as the vector sum of radial component and phi component. I will consider a circle of radius rho naught, a circle of radius rho 1. Without changing phi, first of all, I will go from rho naught to rho 1. What is this? Rho 1 minus rho naught a rho. Now carefully look at it. From this particular point, the phi component is this. The direction of phi will be changing continuously. If I want to move in the mutually perpendicular direction, I will never reach that point. Correct? By just moving in the mutually perpendicular direction from the tip of the first vector, I will never reach the second point. At that point, direction of phi is fixed. But by the time I go to that point, the direction of phi got changed, because of which I cannot really travel in two mutually perpendicular directions. Now, I cannot basically talk about a curved vectors component. It should be a straight vector component. Definitely, I cannot produce. It is not possible for me, if it is there another circle, to travel in mutually perpendicular direction without changing the other components. I have to move along the same radius, right? Without changing the radius, I should change the phi. Can I do that? No. If I go along a straight line path from this point to this point, my radius is changing, right? If this is the point taken, this is the line taken. If this is the line taken, right, its distance from the center is changing, because of which is not defined. Just like that. Check that statement. Next. Very, very important point to be remembered here. But general vector from origin to any point or any point to origin is given in this coordinate system. That will be only a radial vector. Correct? I will be traveling from the origin towards that point. Definitely the direction is radial only, right? Moving straight away from the origin radially to all the intermediate circles that have passed. Listen. From any point, origin to any point, vector is given. Any point will have only rho naught a rho. That's all. Or any point to origin is defined. Vector. What is this? Minus rho 1 a rho. Minus rho 1 a. That's all. Any point, you take this point, you talk about this, because I am continuously moving away from that. This is actually the radial line to all the circles that I have drawn, keeping the center at origin. Continuously in the same radial direction I am moving. So again, rho to a rho. Because I am continuously moving away from origin, it is a rho component only. In the same way, from this point to this point, origin, it is some minus rho 3 a. If I'm from any point, if I go towards origin, negative radial direction. From origin, I go towards any point, it is straight away radial direction. Correct? If I plot a circle through that point, this is only radial direction, right? Everywhere, this is the radial direction. I am moving in the opposite direction or in the same direction. Any point to any other point, there is no vector. If I'm traveling away from it, very, very important for us to know, because most of the problems we will do in cylindrical coordinate system in which one of the components is this. Very important for you to remember. Other component that comes is Z component, mutually perpendicular it is. I component will not come in the general vectors for us. Having defined the vector at any point, dl bar is equal to what? D rho a rho plus d rho is in meter, a rho is in meter, d phi a phi, d phi is in meter. Correct? DL bar. Both are in meter. in the direction of A5. A5 is unit vector. Unit of D5 is not 5. D rho D5, definitely DL bar when I say all the components should be of the same units. Their numbers, the D rho D5. What is DL? Mod DL bar is what? Definitely because they are mutually perpendicular. D rho square plus D5 squared. True it is. It's a vector. Check it once. Hey, I think you understood this, right? Any vector is row component constant, phi component constant at any point, unit magnitude vectors, right? Unit magnitude is in meters actually, right? Don't get confused that A phi is in radian. No, it's a unit vector, right? Check it.